talk about all these fun terms, the equations for those fun terms, and the even more fun graphs for all of these equations. All right, little analogy. Ohm's law, V equals IR. Voltage is the current times the resistance. Very much similar to pressure is equal to flow rate, current times resistance. If you break down resistance a little bit more, it's equal to resistivity times length over the cross-sectional area. We have a really similar thing with Puiseux's law over here. This is viscosity, which is basically resistivity, length over some sort of derivation of area. Long story short is that if you have a small radius, then you're going to have a high resistance. There's not a lot of different pathways for the current to travel. Similar for the blood. So low R is going to cause a high resistance. This would be a vasoconstriction. And the viscosity of blood is also going to be correlating with the amount of resistance that we generate. So anemia, there's not a lot of red blood cells, low resistance. Polycythemia, a lot of red blood cells, more resistance. As we've mentioned before, most of the resistance, really the friction, comes from the arterioles. They have a low elasticity and a very small radius. In the same way that current goes from high voltage to low voltage, blood will go from high pressure to low pressure. And the continuity equation, which is really just saying that there's a, so this is now electricity and also water, the volumetric flow has to remain constant. It is the exact same when we're looking at it with pressure. We'll talk more about this. Kirchhoff's loop rule says that if you go in a closed circuit, you cannot gain or lose voltage. Same thing here is we're not going to gain or lose net pressure. We're going to lose pressure, but we're going to gain that pressure back up at the heart pump. And so the net pressure as we go through a full circuit should not change over time. So same way that friction is going to slowly dissipate our kinetic energy, right? We're losing this to heat. We see a similar thing with high voltage to low voltage. This is being dissipated as heat, which we see in our toaster coils. And it's the same thing with our blood, high pressure to low pressure, dissipating this off as energy and heat. So we should lose pressure. We saw this earlier going from the arterial pressure high, venous pressure low. Is because we lose so much of this energy, mostly through the arterioles. So water is the charge, the flow is the current, and the resistors are really just these narrow areas here. And our water pump can be thought of as a battery or a heart or who cares. So if I'm at 50 torrs over here and then I lose a lot during my resistance where it narrows, I'm now at 10 torrs and I should gain 40 here. So this is Kirchhoff's loop rule applied to water. It also would apply to blood. And of course, it applies to our battery as well, our circuit here. For volumetric flow, so if coming out of my hose is 0.1 liter per second, and you're hilarious, you're a little kid and you're trying to mess with your brother or sister, you put your thumb over the end of this, a lot less fluid can come out, but we have to preserve that 0.1 liters coming out per second. So to remain, it's continuity equation because we must remain the continuous nature of the flow. It's got to come out a lot faster to still be 0.1 liters per second. So we see this when we go from a large vessel to a smaller vessel, things should speed up in the blood. And if that's true, then why is it go slower from an artery, which is large, to a capillary, which is small? I would expect it to speed up. Well, it's because we need to think about the fact that it's not a one-to-one ratio. One artery does not lead to one capillary. One artery leads to thousands of capillaries, shown here. So the aggregate, the integration of all of the cross-sectional areas for the capillaries is actually much larger than it is for the artery. Hence, it slows down, and we want it to slow down because I want effective blood delivery. It's like the FedEx guy driving down your single-lane street, and you want them to be going slow so they can drop off the packages and pick up, I guess, the garbage from all of the houses, the cells along the way. So again, we see that the area goes up and the velocity goes down. Bernoulli's equation, long story short, here we have sort of kinetic energy, gravitational potential energy, pressure energy. The idea is that this is also continuous. So if we're not changing anything with the height, so let's ignore the gravitational potential energy. If what we just said is true with the continuity equation, this should be a higher speed. If this is a higher speed, that means that the kinetic energy component has gone up, which means the pressure should go down. That is exactly what we see. We see a lower pressure in these high velocity situations. This will come back. This is important. And trying to think what else about this. The way I suppose you could think about this is if this is going slow, it has all the time and energy in the world to kind of swing side to side and run up against the walls of this vessel. That is what pressure is. Pressure is just particles banging on the walls. And in this case, the particles, too much of their energy is collaborating. It's directing itself in agreement to go in the rightward direction. So it has less time to bang up and to bang down, which is why the pressure becomes lower. So if you look at an aneurysm like this, the opposite should occur. If it's a large diameter, it should be a low velocity, which means it should be a high pressure. Aneurysms are prone to rupture. Two main types of blood pressure. So if someone's 120/80, it's the systolic pressure and the diastolic pressure. The systolic pressure is when the heart ventricles squeeze, it pushes the blood out. You can feel this in the pulse. And the diastolic is this pressure reservoir with elasticity springing backwards. And the springing backwards keeps a little bit of pressure in the arterial system so we don't dissipate it as quickly. And it just pushes the blood continuously forward. We do not have this as much in the venous system. So systolic, diastolic, pulse pressure is really just the difference. So 120 and 80 would give us 40. Aortic regurgitation. If I have a leaky aortic valve, then that means the high pressure of the aorta is going to push, yes, forwards, but also backwards, back into the left ventricle. This is going to lower the diastolic blood pressure. And so you have a normal systolic pressure, but a much lower diastolic blood pressure, which is said to contribute to this water hammer collapsing pulse. If I was cooler, I could tell you what a water hammer is, but it's some fun tool that I don't know what it is. But you feel a normal pulse, but it collapses really quickly. That makes more sense to me. So the mean arterial pressure, we touched on this earlier, diastolic is twice as long as systolic. So 2/3 and 1/3, twice as long. And so if we want the mean pressure, it's not just going to be the average of the two. It has to lean towards the diastolic a bit. So 2/3, 80, 1/3, 120 gives us 93.33. What's another way of finding this out? Okay, we could also say that the mean arterial pressure is, we just said this, but if we know that the pulse pressure is the systolic pressure is the pulse pressure plus the diastolic blood pressure. That means that we can plug in for the systolic blood pressure this over here. So now I have 1/3 the pulse pressure plus the diastolic blood pressure. When I multiply this out and add it, I get 3/3. 3/3 is really just 1. And so we get this fun equation. So on the test, I think this was a question on mine, was that I had to find the mean arterial pressure, but I did not have the systolic pressure. I only had the diastolic and the pulse pressure. So these are two ways to solve it. You could solve it this way, or you could solve it this way, depending on what you have. I'm going to repeat again. So important that the coronary arteries only fill during diastole. So during systole, we're going to push this up. This kind of closes enough so not a lot of blood can get in here to go to the coronary circuit. On the other hand, during diastole, the large pressure is going to snap these valves shut. And now there's much more ability for the blood to flow down into the coronary circuit and feed the myocardium. More terms, let's do it. Preload is just the blood going into the heart. Often we could say it's the end diastolic volume. So diastolic is the filling period. So the end of the diastolic volume is just when the blood is, the ventricles are the most full. Afterload just means the amount of blood pressure, hypertension, the amount of pressure that we see in the aorta for the most part. And so it's the resistance that the ventricles have to fight to get the blood out. We can use MAP to mean arterial pressure to represent this. So if I want to change my preload, there's a couple different ways I can do it. Venous vasoconstriction. So if you squeeze the veins, remember that's where about 60% of the blood is gonna sit. The blood gets through a little bit with skeletal muscle. We have valves, but if we could somehow squeeze them, there's a little bit of smooth muscle that is going to push the blood forwards, as we can see here. And a dilation one, we're not going to push it as forward. So we're going to milk the blood through. We saw this with exercise, or sometimes we'll see this with exercise. Laying down, so it's hard for the blood to get up here. It's easier for the blood. It doesn't have to fight gravity in this case. We're seeing the same effect in this situation. A leg raise, gravity is going to bring the blood back down to the heart. Squatting is going to propel the blood forwards in addition to changing the afterload. Saline, well, you know what? If you just put more blood, more fluid in my plasma, that's going to contribute to higher volume, is going to be a higher pressure. And something as simple as like RAAS, the RAS system, aldosterone might and ADH might increase the amount of water reabsorbed in the kidneys. That would also increase the blood pressure, and therefore the preload. And then nitrates are going to decrease it. Nitrates are going to cause vasodilation with an emphasis on the venous system. So they're going to decrease the amount of blood going back to the heart. The Valsalva is going to increase the intrathoracic pressure, which makes it more difficult, less incentive for the blood to be pulled in to the right part of the heart, and therefore the left part of the heart as well. So Valsalva and nitrates will decrease. To change afterload, a hand grip is probably the best way. When you squeeze, you're going to squeeze your arterioles, which increases your total peripheral resistance. Nitrates are going to bring the afterload down. So this brings it up, this brings it down. These are vasodilators, and they, as we just said, they decrease, not increase preload. So sildenafil is something that increases cGMP, as do nitrates via nitric oxide. And so they're both causing smooth muscle vasodilation. And I guess the idea is this effect would be synergistic. So if someone is taking sildenafil, also known as Viagra, this would, if you pair this with a nitrate, too much vasodilation is going to cause the blood pressure to drop precipitously, which is particularly dangerous. So if you're an EMT, you often prescribe nitrates. They're also helpful for dilating the coronary circuit so that your heart can get more. So if someone has angina or a myocardial infarction, nitrates might help there. This is, I think, Something's Gotta Give. Great Jack Nicholson, Diane Keaton movie. He's dating this lady and he's on Viagra. And he's in the hospital because he's having like a heart issue. And the doctor puts in nitrates to him and says, "Are you taking Viagra? Because if you are, it's going to be quite dangerous." And his girlfriend shows up and he's trying to look cool, like he's not taking Viagra. And he says, "No, I'm not taking Viagra." And then Keanu Reeves, the doctor, says, "Well, if you are, like, we'll know, it'll kill you." And then as soon as he says that, he freaks out and he rips out the thing, putting the nitrate into his body because he's been taking a bunch of Viagra. It's pretty funny. How do smooth muscles contract? Different than skeletal muscles. We'll go more into detail this in the pharma section, but the contraction aspect, calcium comes in, combines with calmodulin, myosin light chain kinase. It is going to phosphorylate this. The phosphorylated myosin can now contract. On the opposite side, nitric oxide and nitrate, it's going to increase the amount of cGMP, which is going to fuel the myosin light chain phosphatase, takes off the phosphate. So now we have a relaxation. Relaxation is dilation, contraction is constriction. And there you go. Note that this is different than what we see with the skeletal muscle and the MCAT. This is familiar. This is familiar. This is not familiar. This is a weird, different mechanism for contraction. So make sure not to cross the streams and apply all of that old knowledge about muscular contraction towards smooth muscle. It doesn't work that way. Also a little bit different than cardiac muscle as well. So, the classic MCAT, pre-med, undergrad stuff. We send with our brains. It's quite cool. An action potential down our nerves, releases acetylcholine, binds to the postsynaptic receptor. Ligand-gated sodium channel brings sodium in. This causes an action potential to move through the T tubules, where it goes to the sarcoplasmic reticulum, releases calcium, binds to troponin. Troponin shifts tropomyosin. Now the tropomyosin is out of the way. The myosin can bind onto the actin, and this can shorten the sarcomere and cause a contraction. Now, a couple more details, especially ones having to do with cardiac muscle, is that we have these things called DHP receptors, dihydropyridine receptors, which are really just L-gated calcium channels. And so this will allow calcium in. There's something called calcium-induced calcium release. So calcium coming in the phase 2 of muscular contraction, which we'll get to, is going to interact with the ryanodine receptor, which is going to now cause more calcium to be released from the sarcoplasmic reticulum. More calcium being released now does really what we were just talking about, binds to troponin, shifts tropomyosin, etc. We then have this thing called SERCA. So I don't really understand the mechanism of this so much, but it's as if when the calcium, it now binds to the troponin, it's sort of used up, or this is my dumb guy way of understanding it. So to do another muscular contraction, you have to somehow, again, it doesn't make sense because calcium is calcium, but you have to like recycle the calcium. So Circa has to put it back into the sarcoplasmic reticulum. So this is an ATPase pump because it's fighting entropy, and you need the calcium to get back in here. So this is lusitropy, relaxing the muscle so that we have more calcium so that we can push it out so that we can get another contraction. So Circa has a very important role because relaxation of the heart is necessary to have a good next powerful oomph contraction. All of this is really just what I just said. We have the dihydropyridine receptor. This lets calcium in. Calcium binds to the ranitidine receptor. More calcium release. This is calcium-induced calcium release. Calcium now binds to the troponin. The rest is history. Now, notice that we also do have these beta-adrenergic receptors, which, via G-alpha and adenylate cyclase can make CAMP. CAMP makes PKA. PKA can go ahead and interact with the ryanodine receptors, the dihydropyridine receptors, and it can interact with something called phospholamban, which is inhibiting Circa. So it's inhibiting the inhibitor, so we get more Circa, so we get more relaxation. So at the end of the day, this is just going to promote healthy, strong heart contractions. A long story short, for whether you're dealing with skeletal, cardiac, or smooth muscle, more calcium means more contraction if you're ever confused. And this is just a picture of what we just talked about. This is rigor mortis. So rigor mortis is, keeping all of the calcium inside of this, we said requires ATP. And so if I die, I stop producing ATP, and this pump's not going to work for free. So this is very low entropy, and entropy wants to increase. And so if I run out of energy, the calcium is just going to flood out. It's going to flood all over the cell. And more calcium in the cell is going to induce contractions, which is why people's muscles will stay contracted. In addition to that, for skeletal muscle, you need ATP to release myosin from actin, and you're not producing ATP, so it's just going to stay bound. The sarcomeres are going to stay contracted and short. Contractility is the ability to really just generate a strong, stroke volume. So to generate X stroke volume, provided a certain preload and afterload, it's how much oomph you get. As we talked about, catecholamines, beta-adrenergic, beta-1 receptors can interact with these and causes a bigger contraction. The vagus nerve is going to cause a smaller, less contraction, and certain medications can alter this as well. So the stroke volume we said is the end diastolic volume, and then the end systolic volume, and the ejection fraction is really just the stroke volume, how much gets out over the end diastolic volume, how much was there in the first place. Larger end diastolic volumes means more stroke volume. Lower end systolic volumes means, higher of this means negative effect on the stroke volume. Inotropy is just a measure of talking about what our contractility is. So more inotropy, more contractility means a larger stroke volume as well. This is just a good picture of end diastolic volume right before the contraction. And this is right after the contraction. So beginning of systole, end of systole. So preload is measuring this, afterload is measuring this. Inotropy, it doesn't really have direct measurement, but we can see that all of these, increase, decrease. If you think about this, this should make sense. More fluid means you're going to pump more out. More resistance means you're going to pump less out. Stronger heart, better contractibility intrinsically is going to mean stronger stroke volume as well. Cardiac output is stroke volume times heart rate. So my stroke volume is, let's say it's 1 liter, which is way too much. And my heart rate's 60, then my cardiac output is 60 liters per minute. But there's a lot more that actually goes into what the cardiac output is. The heart rate and the stroke volume, which again have their own factors. So if we just look at, real quick, so Ohm's law, P equals QR. Q can be said to be cardiac output. So cardiac output is pressure over resistance, and pressure is represented as mean arterial pressure divided by the total peripheral resistance. Heart rate. So heart rate, you might just think larger heart rate, more pumps means more cardiac output, but it's more complicated, as I said. So notice that the cardiac output's actually going down, and the stroke volume is always going down. Why is that the case? Well, if you're pumping way too quickly, you need long diastoles. Diastole is where the ventricles fill with blood. And if it's not long enough, then you just won't adequately fill the chambers. This is similar to hypertrophic cardiomyopathy or restrictive cardiomyopathy. if you can't fill the heart, then you get a crappy stroke volume, and that decreases your cardiac output. So at a certain point, there's diminishing returns with the heart rate because it can't fill. How do the sympathetic and peripheral or the parasympathetic nervous system affect the heart rate? They are going to mostly affect phase 4. The vagus nerve is also going to hyperpolarize it a little bit, but that's less interesting. Mostly phase 4. So we have this normal, and we have this parasympathetic, and we have this sympathetic. And what you'll notice is the slope here is meh, the slope here is less, and the slope here is more. Based on this phase 4 slope, we'll determine what the heart rate is. We'll talk about this in great detail later up, but this is the main mechanism of controlling the heart rate. So as stroke volume, as we talked about, if we wanted to just imagine what happens with like an athlete during exercise, the preload goes up because skeletal muscle contraction, especially in the venous system, is going to milk blood back to the heart. So increased preload means increased stroke volume. The afterload is up because this vasoconstriction is going to increase the mean arterial pressure, right? Higher, constriction means lower radius. Lower radius means that the resistance is up. So it makes it harder actually to get blood out. Because of the epinephrine and norepinephrine. So that actually is bad if you're thinking about wanting to get more blood to your body. That the contractility is up because of the catecholamines are also stimulating the heart. So this is pro, and this is anti. So how does this, all mix together at the end of the day? It turns out that the catecholamine contractility factor is much larger than the afterload factor, and also paired with the preload as well. So you're going to get a much larger stroke volume at the end of the day if you're exercising. Let's talk about contractility. So the rest of this unit is just going to be looking at Starling curves and venous return curves and putting them on top of one another. So if we look at this curve, the right atrial pressure or end diastolic volume or preload, a lot of these, there's maybe slight nuances, but more or less they're referring to the same thing. And here we have the cardiac output or the stroke volume, again, largely measuring the same thing. And this should make sense. As we go to the right, we're increasing the amount of blood in the heart. And as we go up, we're increasing the stroke volume or the amount of cardiac output that we have. And so we see this general trend. That makes sense. I should be able to output more blood here with a large stroke volume than if I am sitting right there. Now, note that there's many things we can do to change this. We just talked about exercise. This is going to dramatically increase the stroke volume because the increased preload and increased contractility offset the slight increase in afterload. Heart failure is basically when your heart sucks, whether it's systolic or diastolic, we're just not getting enough blood out. Hypertension, stenotic aortic valves, etc. This is going to lower it. We should actually maybe look here for that. This is going to dramatically lower the contractility. But you know what? If you pair it with catecholamines or any sort of positive inotrope that increases contractility, we're going to go from here to here. So there is a bit of a problem. How do we know what the actual cardiac output is? Swan-Ganz catheter really just measures the left atrial pressure to tell us what the preload is. And so if we just put this another way is, maybe we know that we're in the normal curve, but how do I know if I'm here on the curve or here on the curve or here on the curve unless I directly measure the preload? It's hard to know what the cardiac output is with this. So is there a way to figure this out? Yes, obviously. So to do this, we got to understand the venous return curve. So the venous return curve is similar and different, and we're going to mesh them together in a hot second. So talking about cardiac output is the amount of blood leaving the heart. This is more or less talking about the amount of blood returning to the heart. X-axis is the same. So Y-axis is a little different. X-axis is the same. And again, we can just think of this basically as the amount of blood entering into the heart, or the right atrium. So I guess first, if we just look at if the amount of blood entering into my heart is very large, then I should have a relatively small preload. And if we increase the preload, then the venous return goes down as well. So this x-intercept is particularly important, or medium important. Let's not exaggerate. This is a mean systemic pressure. So this is really a theoretical thing. What this measures if there was no movement of the blood, effectively, if your heart stopped, what would be the pressure in your entire circulatory system? And if you think like, okay, well, maybe my arterial pressure is like 110 on it, maybe the mean, and then the mean venous pressure is like 10, right? The venous pressure should be much lower. 10 plus 110 is 120 divided by 2. Maybe the mean is 60, right? Is we just average the arterial and the venous side. It doesn't work like that because remember that most of the blood is actually in the venous system. So it's not going to be necessarily 50-50 weighting. And another way to think about the concept is that if you had blood here, it wouldn't want to go up and it wouldn't want to go down because the pressure has equilibrated throughout the entire body. So the pressure is going to be particularly low for the MSP. All right, now going back to the venous return curve, what if we make alterations to this? So previously we did contractility and heart failure for the Starling curve. What about increased volume? Well, if you increase the amount of volume, yeah, you're going to increase the venous return here. More volume just means more blood's going to get back to the heart. This is straight up. Additionally, we should increase the amount of blood entering into the heart as well. So like the right atrial pressure should also increase. Like these two things kind of go hand in hand if you think about it. Increased venous tone is what we said, like milking the muscle through venous constriction. This is also going to increase the amount of blood coming back to the heart and therefore the right atrial pressure. And on the other hand, if you decrease the volume or decrease the venous tone, it's going to move in the other direction. If you increase the volume, this is also more blood in your circulatory system. At the end of the day, that's really what MSP is measuring. That's maybe the most direct thing that it's measuring is just how much blood you have. Because if you just die and you just let your blood equilibrate and just stand still, more blood in a closed system would mean that there's more pressure. Increased venous tone, I suppose this would mean that most of the blood is in the venous system. And if we have an increased venous tone, then this, or I guess once you equilibrate it, maybe half of it would be in the venous system, but an increased venous tone should increase the amount of pressure, even if you had the same amount of fluid. And then vice versa for the decreased volume and decreased venous tone. Mind-blowing is that the venous return going to the right ventricle and the cardiac output leaving the left ventricle, these need to be equal in most settings. So the cardiac output must equal the venous return. And so we can overlap the venous return curve with the Starling curve. So the x-axis represents the same thing it always did, but now the y-axis represents the cardiac output and the venous return, because again, they should theoretically be equal, right? If more blood is leaving your heart than coming back into your heart, maybe that can happen for a little bit. It can be off, but you can't go your entire day with more blood leaving than coming back. Like something horribly wrong with that. You would die and it's just not possible. So think about it, that should check out. If we put these two things on top of each other, the sweet spot right here is going to represent what our actual right atrial pressure, what our actual cardiac output, what our actual venous return are. And so we can use this to gain an enhanced understanding of everything. So here's our Starling curve. And previously we said positive intratrope, higher contractility and lower contractility. And yeah, this kind of makes sense that, look, if you just kept your right atrial pressure the same, we see that here I have decreased cardiac output, here I have increased cardiac output. But do we really think that if we had a stronger contracting heart that the x-axis, the right atrial pressure, would stay the exact same? No, it's going to change a little bit. So that's where the venous return curve is going to come into play. This is normally what our cardiac output would be in our right atrial pressure. But if you added a positive intratrope over here and a negative intratrope, now it's going to decrease the right atrial pressure, but like we had imagined, it's still going to increase the cardiac output. And this one is going to increase the right atrial pressure and decrease the cardiac output. So the benefit here is just yes, we can still see that the cardiac output increases and decreases, but we can also see by overlapping with the venous return curve how the x-axis is going to shift as well. You're going to do the same thing, but in reverse, right? So I have my Starling curve, but now I want to make alterations to my venous return graph and see how the x-axis would change. So things are going to shift in this particular direction with an increased venous return and whether that's tone or volume increase, and then the other direction if we decrease those factors. Decreasing the total peripheral resistance, nitrates might do this. Both curves will change. So you're going to have an easier time pumping stuff out, which is why the Starling curve is going to increase the contractility, the cardiac output. At the same time, if you have less resistance, it's easier to get everything through the body quickly and in one piece so that it gets back to the heart. So the venous return should also increase. So we see both of these increase, and so this is going to be like hypotension. If you increase the TPR with like a fistula or hypertension of vasopressors, it's going to decrease contractility because it's got to fight everything. There's a large afterload. It's also going to make it more difficult to get back to the heart, right? The arterioles are really squeezing down. It's really just trickling through the venous system. You're going to have less getting back to the venous side of the heart. And notice that the mean systemic pressure stays the same. I'm not actually sure the reason for this. My guess, understanding, could be wrong, look it up, is that the arterioles, as they're, like earlier we had the venous constriction, and the venous system might represent like 50% of everything. So if I have venous constriction, that should increase. Once all the blood is just sitting there, it's not moving, it's just, it's just pooling, it starts exerting pressures, and we said that pressure is pretty low. And if you constrict the venous side, well, now it looks like this. So 50% of it is going to have, smaller diameter, increased pressure. But if you increase the total peripheral resistance, most of this comes from the arterioles. And the arterioles is just, again, the blood is equilibrating throughout the entire body. And the venous might make up like half of that, but the arterioles are just making up a really, really small portion in the arterial system. So that actually wouldn't have a substantial effect on what the mean systemic pressures. Again, that's a total guess. I'm not really sure. So feel free to look it up. I don't think it really matters that much.